So far, we have learned how to get things done without knowing anything about what's under the hood. However, understanding how things work can help us in choosing the appropriate model, right training algorithm to use, good set of hyperparameters, debugging the issues, and performance error analysis. So far, the things have been like black box to us. How does things work and so on. But now, from this session onwards, we are going to dive deep into the underneath. All right, so let's get started. So we are going to learn the gradient descent and all variations and regression and regularization. All right, then we will learn the logistic regression, and a number of discussions roam around the logistic regression. So logistic regression is a fairly interesting topic because the same theory is also used in deep learning. All right. So do not get freaked out when you see lots of maths. I can explain the maths in simple language as well. So, okay. So at any point of time when you are feeling uncomfortable with any of the notations, please feel free to ask. It's completely okay to ask. All right. So, first of all, let's be clear with the notations. Okay. The notations, the first one is M. M is the number of instances, meaning the rows in the training set. Okay, in the training data set, the number of records is called M. For example, in our housing data set, there were 2000 districts in our training set, so M is 2000. All right, now that's the first notation, the first notation you learn. Also, N is number of features, meaning number of columns in the training set. Okay, so we'll understand the notations used in the course. The notations will help us in the understanding of the mathematical equations. Let's take an example of housing dataset in entrant projects. So do you remember this dataset? Here there were rows. These are the records, and these are the features, right? This one is the label. Median housing value is the label, and these are the records. So right, so total number of records in that districts are around 2000. So M is 2000. Xi is the vector of all feature values excluding labels. Okay, so for ith instance, Xi, okay, Xi is the vector, meaning the row in the data set is called Xi. Okay, so there'll be X and then 1, X suffix 1, X suffix 2, X suffix 3, and so on, right? And for the corresponding feature value, it's yi. Okay, so let me go back here. So this is up to here, except for this is x1 up to here, and this one is yi, this one is y1, y2, y3, y4, y5, and these features are x1, x2, including this ocean proximity, x3, x4, and so on, right? So here I goes from 1 to n, not 0 to n minus 1. Okay, most of the mathematical symbols start from 1 to n, while most of the programs start with 0 to n minus 1. Right, they go up to n minus 1, they start at 0, most of the programming for loops. And in case of the mathematical expressions, most of the expressions go from 1 to n. All right, 1 to a number. Okay, most of the mathematical expressions start at 1, most of the programming constructs start at 0. All right, so the first row is x1, no, not x0, and so on, right? For example, in the first district in the dataset, the values are these. Okay, so this is x1, x suffix 1, and y suffix 1. Okay, it's written in a wrong way, so I'll just correct it so that we don't make mistakes. Okay, x1 and y1. right? So far, everything is clear. If the first record in our data set had these values, longitude, latitude, inhabitants, and median house dispatch, then x1, y1 will be this. Okay, is it clear? Now, also notice one more thing, that the bold characters we will be using for vector, while the scalar values will be using italic but not bold. Okay, now capital X represents the entire features along with rows. Okay, capital X is a matrix. It contains all the features excluding labels for all instances in the dataset. All right, so here you can see that x1, x2, x3 transpose. Why? Because this will become horizontal after transposing. That's why we are transposing it. Okay, so first row, second row, third row, up to all 2000 rows. Okay, that's what is capital X. Here it was small x, here it's capital X. Capital X represents entire feature values along with the instances. The rows are called instances, the columns are called features, and the target value is called label. All right. Now, so far everything is okay. Now, the H means hypothesis. H we will be using for systems prediction function. Okay. When we train a model using instance features like xi, we get the predicted value y hat. Okay, so H is that model that we will have to come up with as part of machine learning. We will figure out H. This is our input. Using this input, we will do this prediction. We call that y hat, and we'll compare this with actual y. Okay, so y hat I will be compared with normal y and we'll see how far is this value. Okay, so to reduce the difference between yi and y hat I, we will tweak this hypothesis function. We will try all kinds of hypothesis functions and we will tweak this in order to make this similar to yi, right? This is supervised learning. So in supervised learning, we have a target column, and that target column is what we are predicting, and the predicted value has a hat on top of it, and we compare it with the actual value and bring it down, bring the difference between this and the actual value down by tweaking this hypothesis function. All right, there are many ways of tweaking. We will discuss a few ways of tweaking very soon. Okay, so if the model predicts that the median housing price is in the first district is this, okay, if the median house price, which is the label in the first district is this, so y hat I is going to be 158 400. So we came up with some hypothesis function and we fed the first row. So the first record y hat 1 is this, right? First prediction. The predicted error is y hat 1 minus y1. And generally we use the RMSE, which is the cost function. That's basically root mean square error. So we compute the delta. We compute the error in the prediction, we square it, and then we compute average of all those squares, and then we call that cost function. Question from Deepak is why it is cost function? Because so it's basically a nomenclature. So all we have to do is reduce this cost while tweaking H. The purpose of entire machine learning is specifically supervised is come up with such a H, come up with such a H that the RMSE or any cost function is smallest. So sometimes we may choose some other cost function where we don't like the RMSE and so on. So yes, It's also sometimes referred as error function, but as a correct terminology, we call it cost function. Okay, so mostly the traditionally the machine learning had been looked at as as an optimization problem, and in optimization, the error is generally referred to as cost, right? So probably that could be the historical reason behind it. So in general, we use the lowercase italic font for the scalar values, right? Such as m and y, and for the function names such as h. Okay, lowercase italic values throughout we'll be using, but somewhere we have made mistakes. Okay, lowercase bold font for vectors and uppercase bold font for matrices. All right, and this kind of notation is common in most of the books, because if you read the classic books, you will find that most of those books write in terms of these symbols instead of program. Okay, in program you can't really make something bold or capital, as in you make it capital but not, you can't make it bold. Therefore, or you can't make it italic. So therefore you will be just using y and x and m and capital X for most of these things. All right, so these are the notations, so let's go ahead. About x, small x, y italic, capital X, m, n, h, and y hat. All right, so number of columns is n, and so on. All right, so first thing we're going to do is we're going to learn linear regression, right? All right, let's take a look at the simple linear regression model, right? Imagine that we are trying to predict the life satisfaction, right? Imagine your data set has two columns. One is life satisfaction and other is GDP per capita. Life satisfaction is the label, okay? While the feature is GDP per capita, right? You have only one column in capital X and one column in the Y, right? Now, let's say we want to come up with some kind of hypothesis, right? This is our data. We plotted GDP per capita against life satisfaction. You came up with these values, right? When you draw this data, you have this kind of chart. Now, what you want to do is you want to come up with this line. This is line which kind of predicts it. There could be multiple things you could do at this point of time. You could come up with a curve, you could come up with a line like this, or you could cut it into multiple parts and make a decision tree out of it, right? But for now, for simplicity reasons, we will, or we could use a neural network to let it figure out the relationship between GDP and life satisfaction. Okay, so it seems like there is a linear relationship, it's increasing, right? But it's not really very clear. All right, it's not really very clear. So as here you can see, roughly when GDP is increasing, the life satisfaction seems to increase, correct? And let's say we come up with some equation like life satisfaction equals theta naught plus theta 1 and GDP per capita. A question from Satyajit is, can you explain the feature again in terms of y equals mx plus c? This is your m, right? And this is your c. Okay, those who studied normally using y equals mx plus c. Now, since we are trying to predict the life satisfaction, this is your y and this is your x. So m is not feature here. So I'm talking about your m is a slope. So m is what we have to find out. Okay, m and c is your model. I'm talking about the equation, not m as instances. So like the way we studied earlier, uh, generally we represented the line as y equals mx plus c. Instead of that, we are saying theta naught, which is c, and theta 1, which is m. Why we are saying theta 1, theta naught? So that we can represent it like a vector, right? Theta I, theta 2, theta 3, because there could be hundreds of such features that life satisfaction is depending upon, and therefore there would be more thetas, right? So therefore, we generally get over that y equals mx plus c. All right. So here, Satyajit. So yes, GDP per capita is the x. Okay, is the x. This is y, and this is c, and this is m. Purpose of machine learning is to figure out these thetas. These thetas are the weights. We also call them weights. Okay, the purpose of machine learning or tweaking is come up with those theta naught and theta ones, or we in a mathematical traditional equation, this is c, this is m is the slope, and this is right. Now if you let's take a look at this. Imagine that we came up with some equation. Now if GDP per capita is 0, what will happen? This will be the theta naught, right? This is your this much is the life satisfaction at GDP being 0, right? Now, this is if let's say, right? And if this one is let's say 0, then this line will go through the center, correct? And this one being if the slope is again, let's say 0, what will happen in that case? The line will be flat and life satisfaction will be here for everything. Now, if slope is 1, right? Slope is 1, meaning that, right? So slope is 1, that means it'll have 45 degrees, right? And so on, correct? So I hope you are now clear about it. A question from Deepak is, in case of multi-feature linear relationship, how does the linear equation look like in the typical form? So it look like life satisfaction equals to theta naught plus theta 1 into GDP plus theta 2 into theta 2 multiplied by, say, age group plus theta 3 multiplied by some other feature and so on, right? That's how it look like. Wonderful. So keep asking these questions. These are very important. All right. And we should get used to these symbols, because if you are referring to an algorithm or a book, it'll help you a lot. If you are, let's say, implementing a paper or trying to understand a new algorithm, all of these things would be quite useful. Okay. So because let's say there are more recent works that come into play. So they all assume that you are comfortable with these symbols. All right. Question from Deepak is, how do we represent two features? We represent the features by xi. Okay. So x1, x0, this is like x0, and then there'll be x1, there'll be x2, there'll be x3, and so on. Right. And the features are essentially a list of things, correct? Like an array. Yes, xi is the feature in ith row. X is a vector. X is a vector of features. Okay, xi is the number of the features, the list of features in ith row. Okay, like we did here, this one. Okay, so let's just go ahead here. Say this is one feature, this is another feature, this is another feature. So this is how we represent. Now question is, if you want to say for each row and a particular feature, we basically will have to probably put one more bracket. Okay, but that's hardly ever required. Imagine that we have third row and we want to access the first feature, so it will be x3 comma 1, or maybe x3 then bracket again, and we say 1. Okay, two brackets, bracket 1, bracket 2. But in NumPy, we'll be using the square brackets. Perfect. So this is clear to everyone. So y is going to be theta 0 plus theta 1 into so here again, let me go back here. Good point. Good point. So here, this is going to be a vector. This is going to be a vector. Correct? For every data point, we are saying, let's say, y naught equals theta 0 plus theta 1 multiplied by x of, let's say, x of naught, the 0th value, and then we are picking up a particular feature. So in that way, your way of thinking is right, Deepak? All right. So here I'll say this. Okay. This is how you can visualize. If you, let's say we are talking about individual scalar value, theta naught, y naught equals theta naught. I'm typing in the chat box, theta 1, and then theta 1 multiplied by x of 0, and then the first feature, and theta 2 multiplied by x of 0, second feature, and so on, right? This is how you can think of like this. Okay, I've posted in the chat. So I hope this is clear now. So y naught is equals to this. Okay, and similarly y1 will be equal to the, right? Y1 will be equal to, I mean, basically we are saying that for life status, for particular GDP value, let's say first one, the value on here is this. And we are talking about, this is again, sorry about it. This is y hat, okay? This is y hat. So y hat of 0 is equals to, because it's a function of our hypothesis. In reality, the actual y could be something else, okay? This life satisfaction is basically y of 0, or you can say y hat. Good? So here in this case, we are saying that life satisfaction is a function of GDP per capita. And when we say something is a function, the basic function is maybe a linear function. Linear function means we multiply it by some value and add it some value here, right? And add it some value here, correct? So we are saying that life satisfaction is a linear function of GDP. So we'll multiply, we can get life satisfaction by multiplying GDP by some value and adding some constant to it, right? Adding another number to it. These theta naught and theta 1 are model parameters. The objective of machine learning is to come up with these list of thetas. All right, these list of thetas are something that convert our input into prediction. Once we have come up with the best theta naught and theta 1, then we'll be able to predict the life satisfaction for for the GDP of the countries where we don't know the life satisfaction, but we know the GDP. All right. So for unknown cases, we will be able to do the predictions. So let us say our model has learned the parameters theta naught and theta 1, and these are the values. Then the final equation becomes this, right? This 4.9 into 10 to the power 5 is this is theta 1, and 4.85 is the theta naught, right? A common question is why do we have this theta naught? Theta naught sometimes is called bias. Theta naught sometimes is called intercept. Theta naught is also called sometimes distance from the center. All right. So here theta naught, why do we have? Because if we have theta naught at 0, there is only one kind of lines that are possible, the lines that are going through origin. So if we have line only going from origin, then we may not fit it here, correct? Therefore, we need at least 2 degrees of freedom, meaning we should be able to move this line. Um, uh, we should be able to move this line in a rotational way, like we could try all different slopes, as well as we should be able to hinge it at different point of time, correct? Hinge it at different point of time, as in we'll try first with with zero slope, then some slope, then some slope, then some slope, and then some slope, right? and and so on, right? And then we can do everywhere, right? A question from Robert is, when using dimensionality reduction, are features dropped from X? Good question. Good question. So though we are jumping ahead, but we'll cover that in details. For now, let me just explain what it means by dimensionality reduction. When you have just too many columns, so it becomes really hard to get great results, right? So when you have just too many columns, so it becomes difficult to train coming up with. So the data becomes very sparse and your model is not generally great. So what we do is we do not really drop the columns, but we come up with new set of features. We come up with new set of features such that we have enough information, and we drop that side of the data where there is no variance. Okay, so we come up with new set of features. Like if we are using an algorithm like PCA, it'll generate new set of columns which are more relevant, right? By tweaking the existing columns. Okay, right? A question is, how do we achieve dimensionality reduction? All right. Um, okay, okay, this is a hard thing to do right now, but let me give it a shot. Though we are jumping ahead, but don't worry, I'll make it worthwhile. All right. A question is, how do we achieve dimensionality reduction? A quick question to all of you. In your normal life, in your normal life, do you change 3 dimension to 2 dimension? Anything you do? Anything you do? Yes, thank you, Jay. Thank you, Deepak. So, and yes, Satyajit. So whenever we draw something, take a photograph, or even see something, we're converting three-dimensional things, information about our three-dimensional things into 2 dimension, right? Or we're looking at somebody's shadow by throwing a light at it, correct? That's also converting a three-dimensional object into 2 dimensional object. Is everybody comfortable with that idea of 3D and 2D? Okay. So Tejit, I'll come back to that one very quickly. Okay. And but let's just go with this example that when we are taking photo, we are converting 3D into 2D, right? Now, the art of photography, if you look at it, what is it that we're trying to do? From which side do you take photo? From which side do you take photo? Which axis do you drop? Front view, right? Why do you do that? There are many ways to take photo. You could take photo from the head. You could take the photo from the right. You could take the photo from the side, or you could just take photo of their feet, right? There are so many ways. Why do you take the photo from the front? Correct, because it depicts the max of human view, right? So this is exactly what is called dimensionality reduction. What we do is we move the camera to a direction such that our 2 dimensions are giving us maximum information, right? Our two dimensions are giving us maximum information. Similarly, when we're talking about PCA, what is it that we do there? We move the camera, let's say we are trying to drop one dimension, but we don't know which dimension to drop right now. So what we do is we move the camera and we convert n to n minus 1 dimensions. Then we convert that n minus 1 to n minus 2 dimensions, and we keep on reducing the dimensions, right? We keep on reducing the dimensions. So that's exactly is dimensionality reduction. The PCA exactly works like this. It moves basically it figures out the new dimension of maximum, what do you call, maximum variation, and then it keeps on dropping the one from which we have just realized that there is a maximum variance achieved. A question from Satyajit is, but how far can we go on reducing? When we are taking a photo, we are losing information, right? We are losing information. So we keep on reducing, we keep on dropping the excesses where there is not much of a variance. All right? So that's exactly, we will go into more details about algorithm, but for now, you can understand that dimensionality reduction is more like taking a photograph. Okay, so we move our camera, we roam around, you know, uh, and we try to figure out that dimensions, those set of dimensions. We tilt the camera, we sometimes do all of that just to figure out those dimensions that cover the maximum variance. Okay? All right, I hope everybody is clear about dimensionality reduction, at least this much. Our object has three features, X, Y, and Z, like three coordinates, and every part of it, right? Now, when we moved our camera, we basically ended up with the X and Y, right? Right? Moving. All right, it is clear only to Deepak, Satyajit, and Robert. It's not clear? Okay. So we'll dive deeper into dimensionality reduction and understand when to use it and when not to use it. What are the advantages? And also we will see the mathematical properties of dimensions, like why can't human visualize more than three dimensions, right? And trust me, if somebody is telling me that they can visualize more than three dimensions, they are of course lying. Okay, so we will talk about it in more details. All right, perfect. Moving ahead. So what does this equation mean, right? Point from Deepak is that it's a linear relationship. That's correct. It's dependent only on one variable. That's correct. And it's positively related. Positive related, why? Because do we know that the slope θ1 is positive? Because we saw the data. That's right. So we can find the life satisfaction value of unknown GDP per capita if we find θ0 and θ1. Okay. So given the GDP per capita, we can predict the values. Perfect. This is the general equation of line that we have already studied. So we used to represent a line like this, y equals mx plus c, and y is the result of multiplying. So anywhere, wherever we had this proportional relationship, we said y is a function of x, linear function of x, we always would put it this way. But if we have many such values like x1, x2, x3, x4, x5, then then we will not be able to represent it using a line. Instead, it will be a hyperplane, right? It'll be a hyperplane, right? So what if y-intercept is 0? In case we force it to have theta 0, then we'll only have lines going through the origin. And okay, so I hope this is clear. This is a common interview question. That's why I put it here. Now let's go back to Entrant project. If we build a model for predicting house prices, housing prices using these attributes, longitude, latitude, inhabitants, and median income, then our equation will become a little more complex. This is how it would be, right? Predicted house price is equals to theta naught plus theta 1 multiplied with longitude plus theta 2 multiplied with latitude, theta 3 multiplied with inhabitants plus theta 4 multiplied with median income. Notice that the theta naught is only one, not separate from each of these values, right? So this is the way we represent the plane, or you can say for multiple features, if you want to do the prediction, this is how we do, right? If you think about it, this is going to be like x-axis, this is going to be y-axis, this is going to be z-axis, and this is going to be some fourth axis, and this is the fifth axis, okay? So we are trying to predict a value using other things. So if you think about the axes, it might look confusing, but for now you can just think of it this way, that to get to the house price, we'll have to multiply something with longitude, multiply something with latitude, multiply something with inhabitants, multiply something with income, and then we will add some constant to get to the outcome. Okay, this is a linear relationship. Linear relationship has been observed to work on many kind of data sets and is the simplistic way of getting to the results. Linear regression is this. This is called linear regression, whereby we assume that the relationship between input and output is linear. There's no square, it's not longitude square or latitude square. All right? Or more precisely, this is how we write. Okay, this is how we write. So the y hat, which is the predicted value, is equals to theta naught plus theta 1 multiplied by x1 plus theta 2 multiplied by x2, and so on, right? Also notice that this is basically going to be a constant, and so are these other constant values, while these x1, x2, x3, and so on, they're going to be the what do you say, this is going to be a vector. So each of the value is essentially a dot product of theta and x, right? So if there was no bias term or an intercept, we'll have only the lines that are going through the center. Okay. Bias term is a constant and does not have a feature. A question from Deepak is, what if the relationship is not linear? How do we know that before applying linear regression algorithm? Is it by statistical visualization? All right, good question. Let me ask you this. Imagine that there is linear relationship. Sorry, imagine that there is no linear relationship. Okay. And we are trying to we come up with a linear regression with the minimum error, right? We come up with this equation, or we come up with thetas, and but it has good error, okay? So do you think if, let's say, our equation is not fitting the data, will it have high error on both the test set and training set? Correct. So a linear regression will have high bias. Correct. So when we compare multiple such models, multiple such models, say one is linear regression, other is say descent trees, another is say SVM, we will know which one is giving the smallest error, right? And we will use that. Okay, smallest error on both the training and test set, we would know which one has high bias or is it overfitting. Is it, um, if something is having, let's say, um, right, big error even in the prediction, then definitely that model is not good. Okay, but if something is not having error in the outcome, you generally take a look at the training data predictions as well. If training data predictions are also high, we call that the model is, if let's say the if your model is doing great on the training data but not on test data, then that's overfitting. Otherwise, it's underfitting. So linear regression will be underfitting in case it's not fitting your model, because linear regression is extremely simplistic model because it has only few degrees of freedom. Okay, therefore we will go for a complex model. Okay. All right. So question is, how do we figure it out? By visualization, or is it by, um, it's a hard call, but yes, visualization is a great option. Okay. And so we learn about how to do nonlinear regression as we go ahead. Okay. We will see how to do the high degree polynomial equation relationship. All right. So we'll see that very soon. Going ahead. So, right. So the general equation that we just studied was that y hat is a function of h, and is an outcome of h, which is hypothesis, and h is nothing but a function which is called on x, right? Or in the linear algebra way, we can represent all thetas as theta and put t on it, and then we have x, correct? So all right. So what does it mean to you, this one? Okay, in case you are not comfortable with this idea. So, all right, let me just show you what it means. All right. So when we are saying theta dot, this is dot, and this is small x. Okay, this is small x. So theta dot small x, what does it mean? It means that, and here there is a t on it. Okay, now this essentially we are saying theta means what? Theta naught, right? And theta 1 and theta 2 and so on, correct? So when we say theta t, what does it mean? It means we are converting it into horizontal, right? Theta naught, theta 1, and theta 2, correct? And then we are saying there is a dot product with x. Okay, by default, whenever we say a vector, this is like a vector. Okay, x is say first feature, x naught. Oh, sorry, this is, okay, this we are going to put one extra one here and say this is first feature, x1, x2, and x3, correct? These are the columns, x1, x2, x3, and we add extra one here. You will see that very soon. And when we multiply this too, so this gets multiplied with this, correct? And this gets multiplied with this. This gets multiplied with this, and so on, right? Here there'll be, let's say, theta 3 also. So it'll be theta naught plus theta 1 into x1 plus theta 2 x2 plus theta 3 x3. Okay, so this y hat, okay, is equals to this in case of linear regression. This is a dot product, correct? Dot product means each of these values are going to be multiplied with corresponding, right, in the vectors. If you have one vector and another vector, this is what you're going to do. Perfect. Now you understand why there's a t on it, because theta means this. Theta means a vertical one. So when we say theta t, it becomes horizontal, and x means vertical ones. But this x is a little different because it has an extra one here. Okay. All right. Everybody comfortable with this? So we are saying that we will come up with H hypothesis of theta means this is our model. We're going to come up with some hypothesis having some thetas so that our prediction is as precise as possible. Now, for linear regression, this hypothesis is basically equivalent of theta dot x. Yes, is that one bias? This one is basically theta naught is the bias. Okay, and one we are adding for this theta one, theta naught. We call it bias because this is the one which moves us from away or near to the origin. Okay, all right. Al-Sayed, Arun, Deepak, Jay, Nikita, Prashant, Robert, Satyajit. It's actually extremely simple thing, just that we are not too used to looking at symbols. So it looks kind of alien to us. Okay, so make yourself comfortable with these symbols. Okay, if you have doubts right now, ask those doubts. I would love to clear it now. I mean, trust me, even very senior persons, even the people who are really good at maths, they also don't like to look at symbols that much as they like to look at the text or images or any other things. Okay, because text we learned very early in the childhood, and symbols we learned really late. All right, so theta t dot x is the dot product of theta t, and theta t is in theta transformed from vertical to horizontal, and x. H naught, h theta is the hypothesis function using the model parameters theta. H naught fits the model and calculates the weights. So when we are doing machine learning, essentially we are trying to either figure out h theta or we are trying to fine tune thetas. Great. So question is, let's say we got this, but how do we train it? How do we train it? So training a model means setting its parameters, figuring out those parameters so that the model best fits in the training. For this purpose, we first need a measure of how well the model fits the training data. And as we have seen in end-to-end project, there is something called root mean square error or mean square error. There is something called mean absolute error, in which all we do is we subtract each value, compute the positive values of it, as in if there is a negative sign, we just remove the negative sign so that one negative does not cancel the another. So there is something called mean absolute root. So we call it mean absolute error instead of mean square error. Okay, you will see that in some cases we use the mean absolute error as well. Instead of squaring it, we basically remove the sign from it in case it's negative. All right, in each of the errors, let's say we compute the first instance, we got some y, that's a predicted y, and there's actual y. Then we did the same thing on the second row, third row, fourth row, and so on. So we got a list of errors, correct, on each with respect to each of the rows, each of the instances. Now to come up with a single number, what we do is we basically square each of these values, sum it up, and divide by the total numbers. That's computing the average, and that's called mean squared error. Mean mean squared error and root mean squared error. Here there is a d, here there is a d, here there is no d. Okay, so let me just fix it. That's a little weird, right? Now, question is, how do we train the model? We will use MSE, mean square error, for training the model in this session, right? And why MSE? It's simpler to minimize MSE than root mean square because computing square root takes a lot of efforts. All right, those who are not aware of MSE, let me just say mean square error is the, let's say we are trying to predict, let's say we are trying to predict the house value just based on the house area, and we have a single variate regression. That means there is only theta naught and theta 1, and in that case we are going to just draw a straight line, right? Let's say we come up with this straight line and we find the error from actual point. So given an area, this was the original as per our model, this is our model, this is the prediction, and this delta is the error, right? So what we do is we square each of these values and then we sum it up. You see sigma. Sigma means go to each of these values, this, and square it. And after squaring, you do the summation. The sigma means sum up all these values starting at first instance up to m. Remember m? M is number of instances. Here, how many instances are there? 5 instances, correct? And then we divide it by m so as to average it out, and that becomes our mean square error. Is it clear? Is it clear, everyone? This formula, this is the first time you're seeing the formula, and you'll see this formula more often as we go ahead. All right, so while training the model, we have to find the values of theta that minimize the mean square error. Okay, so essentially this is the mean square error, right? Is it clear? So theta t, so this is our y predicted, correct? Is everyone clear about this? Feel free to ask. So this is your theta t dot xi, right? For each of the instances, all right, sure, don't worry, Satyajit, that's what we are going to do slowly, okay? All right, so this is theta t, dot xi, meaning ith instance, ith row multiplied with thetas, then we are subtracting the predicted value of ith row, right? So for first, let's say for the first row, we're going to do this, and then we square it, and then we sum it. Okay, for each of the record, we compute it and then sum it. The MSE is a single value. The X here is the list of features. Xi means for ith row, all the features. Correct. Theta is a vector. X is a vector, while Y is a scalar here. Yi is a scalar. Xi is a vector, and theta t is basically the transpose of thetas that we assumed. Initially we'll start with some random values of thetas and then we'll optimize those. Okay, so MSE is this. Okay, MSE is this. Is it clear, everyone? So our purpose is to come up with those thetas whereby this overall value need to be minimized. Okay, it's a pretty simple thing if you think about in terms of physical ones, that we assume something like this is the line that is going to fit into that. Then we basically find the error, okay, after predicting, we assumed a model. Using that model multiplied with the input features, we come up with the prediction, compare with the original, and then square it. right? All right. I'll say Arun, Deepak, Jay, Nikita, Prashant, Robert, Satyajit. Please feel free to ask at any point of time. All right, and keep asking the question because I'm really, worried generally in the beginning of the maths. Okay, because we haven't seen this kind of sigma for very long, and it scares us. All right, there's nothing. I mean, that's the truth. Okay, and or even if it doesn't scare us, we are not quite used to it. The moment you look at it the first time, you kind of feel that we are out of place. Okay. So question from Arun is, can we understand MSE with an example? All right, this is a good example. So imagine that we are trying to plot house value against house area. So, and we thought that there is a straight line that's going to fit into it. And now, but this straight line has got errors, right? For this value, for this point, our straight line is predicting this value while originally it was 2. Here it is predicting 1 while it was some other value. Sorry, it is predicting this value while it was 1. The line is predicting this value while it was this. For different house areas, these are the values that it is predicting while originally it was something else, right? So what we do is we find the overall error, because stating the error in non-scalar terms, meaning stating a list of error, does not make any sense. Therefore, what is done is we basically subtract the original. This is the error in each of the numbers, right? This is the error in each of the numbers, right? And then we square it. Why do we square? So that the error in each point gets magnified, and also the negative sign is gone, because this is a negative error, this is a positive error, they'll cancel each other, right? That's not right. That's not right, because error is an error and error should not be cancelled with another error, right? So we square it and then we basically compute the average of all these. This square of these is, this is called mean squared error. We have we been doing the, had we been doing the mean absolute error, in that case we'll just change the sign of these two parts and sum up all the errors instead of squaring it. All right, and that's it. So that's what is the the mean squared error. Now you can see that this is the error. Now what was the why I predicted? Why I predicted was, why I had was x into the theta t dot x, correct? Theta t dot x. So that's what we have written here. All right. So the mean squared error for, let's take an example. This is our xi. This is, we are just picking up one row, and this is our y predicted. This is our x predicted, and we can just okay. So how much is the error? This minus this. Sorry, median house value is this. Okay. All right. We can actually compute it. Okay, it's not mentioned here. All right. So while training models, we have to find theta, which minimizes root mean squared error. Right? There could be many other ways of measuring error, but right now, in case of regression, we are going to mostly use the root mean squared error. Let us understand how the training of linear regression model done internally. Okay, there are two approaches to figure out or train the linear regression model. When we say train, we are basically going to find out those thetas or those lines that fit our data, right? One is using normal closed form equation. Other is the gradient descent approach, right? Other is gradient descent approach. There is a third one also. Those of you know this one. Okay, let me, uh, okay, all right. So be with me here. Let's say we have on x as 1, we got 2 here, right? This is 1 point. And let's say x as 2, we got, say, 4. All right. So if I ask you what will be the value at x equals to 3, what will be the value? What will be the value of y? Let's say this is our y, this is our x, and for x1 we have 2 as y. For x2 we have 4. Okay. Now what will be the value at x equals to 3? 6, right? For x is 1, the y was 2. For x is 2, y was 4, and so on. Correct? All right. All right. So we can say for x is 1, let's say we have theta naught. Correct? So theta naught plus theta 1 equals how much? 2, right? And theta naught plus twice of theta 1 equals 4, right? So you can see that when we solve these equations, this is getting cancelled, right? And we subtract this and we find out minus of theta 1 is minus 2. So theta 1 is 2, correct? So for x equals to 1, y is 2, okay? So if our equation was this is y and then we say theta naught plus theta 1 into x, right? So for x equals to 1, we got theta naught plus theta 1, which is 2. And for x equals 2, we got theta naught plus 2 theta 1 equals 4. So we got theta as 2. All right, is it clear, everyone? So and also when we put it back here, we get theta 0 equals 0, correct? Therefore, our equation is y equals 2 of x, right? Now, here the story looks really beautiful, but the problem occurs when things are not in place. Okay, things are not in place when the moment things start slipping off a little bit. Okay, things start slipping off a little bit. Now, let me just take another story here. So let's say, okay, for value as 1, 2, 3, 1, 2, 3, here the value was, let's say, okay, so let's say the value was 2, okay, for this, all right, and for 3 and 4, okay. So for the 2, basically, let's say the value is 3.5. For 2, the value is, say, 3.5. This is 3.5. This is 2. Okay. And this is, let's say, 3.5, right? 3.5. All right. So for value 2, the y is 3.5, while for 1, it's 2, right? And for 3, something weird happened, and it's, let's say, 4. Okay. Let's say this is 4, this is 3.5. Now, here you can see that what we, I mean, if we are given this kind of scenario, what is that we're going to do? Okay. Let's say we come up with same thing as, like, let's say y is a function of theta naught plus theta 1 into x, correct? So we say that here the 2, right, this 2 is theta naught plus, this 2 is basically theta naught plus theta 1 and 1, and 3.5, that's the second data point, is theta naught plus, Okay, theta naught plus what was the value? Theta 1 into 2, and 4 is theta naught plus theta 1 into the into 3. All right, so we got now two variables to find out, theta naught and theta 1, while there are three equations, correct? So as we did earlier, we could draw the line with two data points, this, this, or this. We could draw three possible lines, but that would not solve any problem, correct? Like earlier, what we did was we took two data points, we draw them and so on, and we found the outcome very easily. But in this case, it's not really, that straightforward. We can't really just go around and find their exact values, correct? So the idea is to come up with something like this, right? Somewhere. So in this case, there's going to be some error. We can't really come up with theta naught and theta 1 so that it's exactly y. There will be some amount of error, right? So in the first case, there will be some amount of error. We came up with theta 1 and theta naught. It can't happen because there'll be some amount of error. So there won't be an equality here, right? So there will be an error here. There'll be error here. There will be error here, right? So what will be the overall error here? Anybody? So the overall error is going to be theta naught plus theta 1 minus 2 square of it plus similarly theta naught plus theta 1 into 2 multiplied by 2 minus 3.5 square of it. And what will be the error in the third case? Third case, the error is going to be theta naught plus theta 1 into 3 minus 4, right? So the idea is that it can't be equality because it's not possible to basically fit it, right? There is no single line that can fit through all these three data points, okay? There's no single line that can fit through all these three data points. We can draw a straight line here, a straight line here, or a straight line here, but we cannot draw a single line going through all of them, right? Therefore, whatever line we draw will have some error because of this misplacement, or this distance, right? If we are lucky, all these three data points are exactly in the straight line, then these three data points will have the single straight line. If you are really lucky and your data is having a perfect linear relationship, but in reality, it never happens. Therefore, what we do is we come up with a line, right? Right now we are doing algebra normal one, right? We are saying that imagine a line with theta naught, theta 1, compute the error because of the first point. This is what the error is. Similarly, compute the error because of the second point. Compute the error because of third point, right? Is everyone with me so far? Al Sayed, Arun, Deepak, Jay, Nikita, Robert, and Satyajit. This is a very important part. So the first case, the zeroth case, was beautiful because we could just, eliminate the variables, and we were happy because we found the perfect values for thetas, right? But here, the challenge is that these three data points are not in line. Yeah. So what we did was we came up with some line. Let's call it theta naught, theta 1, and then we said that okay, we draw some random line. Sorry, we came up with some random line with theta naught, theta 1. We are doing algebra right now. We're just putting the symbols as such. And we are saying that error is this, correct? Now, what is the purpose of this exercise? Purpose of this exercise is we want to minimize this error, correct? We want to minimize this error. And how did we ever minimize this error? Anyone? How did we ever minimize the error? We are trying to minimize this error by tweaking these theta naught and theta 1. We need to come up with those theta naught and theta 1 such that this error is minimized, right? Right? I'm going to draw another one. Okay. Imagine that this is your error. Imagine that this is your error and this is your theta naught, right? And let's say it is something like this. Let me just do it again. Okay. Oh, this is crazy. So this is my error, right? And this is my theta naught. Okay. Imagine that as theta naught is increasing, the error is dropping, and then it goes up, right? So there will be, we have to find out this value of theta. What is this value of theta where error is minimum? Correct? Is it clear? That if we draw, if you go back to this, if you go back to this, not this, yeah, not this, okay, all right. So let's say this is my error. It has some relationship with theta, and it is definitely a square one, so it's kind of a parabola. It's going to be like this, right? Now, let's say we want to find out that value of theta on which this E is minimum. How would we go about it? Anybody? So here at this point, the slope is how much? Positive or negative? Negative, right? And as we are approaching this point, what happens to the slope? As we are approaching the minima, what happens to the slope? Zero, right? And how do you compute the slope? Yes. How do you compute? Given, let's say this is going to be some kind of, theta square plus theta 2x plus something, right? That's right, Robert. So this is what we are going to do. We're going to compute the rate of change of theta naught and equate it to 0, right? That will be the point where the error drops down to 0. And for that, we will, when we do this, we'll compute what is the value of theta and so on, correct? Similarly, since we have two variables, we will also do rate of change of error with respect to rate of change of with respect to theta 1, and we will also compute theta 1 from there. So now we'll get two equations. One is from this, other is from this, and we'll solve those for theta 0 and theta 1. All right. So if we go back here, so when we differentiate this with theta naught, okay, so when we differentiate this with theta naught, what will happen is we'll get, anybody can help me, twice of theta naught, twice of theta naught plus theta 1 minus 2. This is theta 1. My handwriting is really poor. And plus, we say twice of theta naught plus theta 1 into 2 minus 3.5. Then I say plus twice of, I say plus twice of theta naught plus theta 1 into 3 minus 4. Correct? So all we did was very simple thing. All we did was we took theta naught, theta 1, computed an error. We differentiated error once with respect to E, and once we will, sorry, we differentiated error with respect to theta naught. Similarly, we'll do that for the theta 1, right? And we equate it to 0. Okay, so we got one equation because of this. Okay, and one equation because of another, right? So this will be, let's say, uh, all right. So theta naught plus theta naught plus theta naught, which is thrice of theta naught, correct? Then we say plus theta 1, twice of theta 1, and thrice of theta 1, which is 6 of theta 1 minus 2. So there'll be 6, there'll be 9.5, correct? And similarly, when we differentiate it with respect to theta 1, we will get a similar equation, right? We will get a similar equation, and it'll be the extra 2, extra 3 will be here, right? So how can I quickly calculate it? So it's going to be extra 2, extra 3, okay? So it's going to be twice of theta naught and thrice of theta naught. 2 plus, so 3 plus 2 plus 1, which is 7, right? No, it is going to be 6. 6 of theta naught plus here 1 plus 2 into 2. Yeah, 2 into 2, which is 4, that is 5. 5 plus 9, 14 theta 1 minus. Now this in the same way, this is going to be 2 plus 7, that is 9. 9 and 4 into 3, which is 12. 9 and 12, how much? 21 equals to 0, right? When you differentiate it with respect to theta 1, this 2 will be multiplied here, 3 will be multiplied here, correct? And of course, the usual 2 will be there. So you try doing that. Now what you got is 2 equations, correct? We got 2 equations. We can definitely solve it for theta naught, right? And we can also solve it for theta 1. We can also solve it for theta 1. So with this way, we will get theta naught and theta 1. Is it clear, everyone? So this is our E, the error. This is our error. We differentiated once with respect to theta naught, and then with respect to the theta 1, and equated it to 0, because of which we got these 2 new equations which we can solve. What is it that we're trying to do? We're trying to say that find the error, which find the rate of change of error with respect to the first by varying the theta 1. So it is essentially saying that we are varying theta naught. We are varying theta naught. We are varying theta naught such that the rate of change of error is going to be 0, right? Similarly, we are going to vary the theta 1, and right? But here we are doing the normal algebra, okay? Because we know clearly that our relationship here is linear. Here is linear. Imagine that it was like cube. If it was like cube, this was square, this was 4, we can't use this method, okay? So this is called the normal equation way. The first one was the case where the life was really beautiful in the sense that we could just use 2 consecutive equations, cancel something, and get the values of various thetas, right? But that's not right. That's not possible in the case where approximation is required. So what we do is, for approximation, we come up with the formula for E, the error. We differentiate the error with respect to all the variables partially, and then individually or partially. Then we come up with new set of equations that we can solve. This is called normal equation. Okay, using this we can really find the perfect theta zeros and theta ones that give us the minimum error. All right, provided our data has linear relationship. So is it clear only to Robert and Deepak? Satyajit, Nikita, Jay, Arun, and Al Sayed. So does it make sense to you? Is it clear that if we want to find out, um, if we have an equation of something and we want to find out the minimum value of it, then we just differentiate it. Question from Deepak is, while differentiating, there is no d theta 1 plus d theta 2. We are saying that they are not changing with respect to each other. So rate of change of theta 1 with respect to theta 0 is 0. Okay? Because those are two kind of independent values we are coming up. That's assumption we are making, yes. So essentially we are saying is first differentiate E with theta naught, which means theta 1 is kind of constant. And then we'll differentiate E with respect to theta 1. In that case, theta naught will be considered a constant. All right. So when you generalize this equation, you would get normal equation. All right. You will get this normal equation. All right. We'll continue from here after the break. Okay. Break for 10 minutes and back by 8:46 a.m. IST. So far, we learned something really interesting. Something really interesting. We learned the derivation of the normal equation. The one that we went through, that we differentiated error with respect to thetas, right? That's essentially a derivation of this equation that you see on the screen. This is called the normal equation. This is great only if you have the linear relationship in your data. Second, your one is your data has a linear relationship. Second, when you have few number of thetas. Okay, few number of thetas, because remember that the way we did, we had to differentiate E with respect to theta 1, then theta 2, theta 3, theta 4, and so on. If you have so many thetas, you will have to differentiate so many times. And once you have differentiated, you will have to solve those many equations concurrently in order to get the results. That's why this normal equation is actually great if your data has few number of columns and your data has linear relationship with linear relationship with respect to the outcome. All right. So normal equation can give you great results if you are okay with linear relationship and you have few columns. So here what we do is the way we compute thetas, the thetas, you see, the right, you see hat here, you see hat here. Hat means those thetas that minimize the cost function. Cost function here is the mean squared error. So what we do is whatever x we have, we transpose it, we do a dot product. Okay. After doing dot product, we do the inverse of it. Okay. And then we multiply it with x transpose and then multiply it with y. All right. So this X is the training data set. All right. So we can give it a try. All right. This is essentially derived from the same thing. Solving consecutive equation is called computing the inverse of the matrix, right? That's why we have an inverse of the matrix here, and so on, right? So I'm going to walk you through this. All right, let's launch this example here. Okay, this is going to be quite useful to you. All right, for now, we can actually by heart this equation, right? So xt dot x and the inverse of s, okay, and right, and then we have xt, okay, dot xt dot y, okay. All right. So this I don't know how are we going to memorize it. So great, but it's actually very simple when it comes to NumPy. Ideally, we should be talking in terms of NumPy rather than um, rather than this mathematical equation, because mathematical equations look very scary, while the Python one, the NumPy one, is far more simpler. Okay, so first of all, we import NumPy, then we basically generate some data. You see, here we've generated some amount of data, right? This is random number, so we are saying that generate an X with this kind of size, right? And so basically 100 rows and one column is what it's going to have, right? Then we are saying y is equals 4 plus 3 and so we are creating hypothetical data by ourselves. We know that there is a here we're generating y as a function of 4 plus 3x and adding some noise to it. Okay, we call this noise as Gaussian noise. Okay, so let's just get started, and here we go. All right, so we have the normal equation and training models. Where is training models? Training linear models. All right, let it load. I understand that we have gone a bit into maths, but I'm sure that this is going to be a very helpful thing for you. Okay, and I hope everybody is comfortable with what we did as part of that exercise. I did not go into solving each and every part. All right, I'm just waiting for it to load. So that's okay. All right, the kernel is ready. Now it's basically going to run. All right, so this part is normal standard setup code, and this is where we have. All right, done. I'll just clear the cell data, probably that'll help. Because it looks like this is too heavy on the browser. Cell outputs and all right. So first of all, the setup part, let's just run it. Okay. Now here, what we are doing is we are first generating X, then we are generating Y. And when we plot it, this is how it looks like. You see that? This is how it looks like. There's an amount of noise we have added to the normal equation. All right. Not, I mean, usual 4 plus 3x equation, right? So ideally, theta naught should come out to be 4 and theta 1 should come out to be 3, even after we have added the noise. Okay, so this is our data with a lot of noise and a lot of errors. Now when we use the okay, I'm going to skip it here. Those who are wondering what's happening here, basically it's generating 100 random numbers with one column. So 100 by 1, the shape of x is 100 by 1. You can see shape of x is 100 by 1, shape of y is 100 by 1. And if you want to fill something of that size and create, you can use np.ones. And if you want to concatenate, you can add 1 to all those values. So here, what we have done here is the x that you see does not contain the 1, right? So what we have done is we have added 1 into the x. Remember that we did it in one of our exercises, whereby when we said theta dot x, we need to add 1 into x, right? So we have added 1 into x. Okay, so all we did was created one column and concatenated X and that one. All right. Afterwards, we have this value, right? Afterwards, XP represents the value with 1. All right. Now, this is our normal equation, right? So we are saying there is a function called INV. INV computes the inverse. Dot T computes the transpose in NumPy. So first of all, we did XB dot T. Then we multiplied with XB, right? So XB transpose of XB multiplied with XB, right? So if you take a look at, all right, let me just show you the normal equation. So this is what we are doing. So first of all, we created X by adding one as extra column, right? And then we did transpose of it, right? Then we did transpose of it. You can see we did transpose of it. And then we multiplied by XB. We did the dot product with XB, correct? And afterwards, we did inverse of it. Then afterwards, we applied inverse on it. Okay, so this is where we are up to this point. Okay, we can make it further simpler. Okay, we can define a variable called XX. Okay, and something like this, and use that XX here. So we are saying that this value dot product with xt and then y. So this value dot product with xt, right? And then dot product with y. Okay, now you can see that the line that it has come up with is 4.2 and 2.7, right? The theta naught is 4.2 and the slope is 2.7. You can see that this is exactly, this is not exactly, but this is similar to what we started with, right? 4 plus 3. So instead of 4, it's saying 4.2. Instead of 3, it's saying 2.77, right? So it is able to kind of approximate the value of the line that's going to fit through this data. If this value was 10 times than this, then you can see this will have a far more. Now you can see this time the results are far better because the noise is less compared to what? Okay. All right. Going back to here, you can see a question from Deepak is this difference is because of the noise we added? Correct. Because of the noise we added. So here imagine that we have some value of X, some value of Y, right? And the Y value, while computing this value, we have added some amount of noise. Okay, because of which data being, if instead of being straight 4 plus 3x straight line, it is basically drawing that straight line. Okay, instead of drawing that straight line, it's trying to approximate that straight line. All right. Okay, so you could try this out, right? You could try this out. So it says that the value 204 are not aligned here, right? So probably, I see. The reason is that we have defined x1b here, and we have y, which is 4 variables. Okay, 4 values. So we are saying xb dot x1b, right? Oh, I think the error is this. Okay. All right. So I hope everybody is clear about normal equation, right? So we learned that in case our data is very, we have just two records and we need to figure out a straight line, then we can just do the variable elimination and we can come up with that. But if our data has a lot of noise and it looks like it is linear, then we can use the normal equation. All right. So, and once we are done with coming up with thetas, then we can of course do the prediction, right? All right. So this is what we just did. So weights in the original equation were 4 and 3, and 4 was theta 0, and theta 1 was 3. But in our example, the answer we got was approximately theta naught. Theta naught was 4.14 and theta 1 was 2.8. Now here you can see that the problem with reproducibility, because here the we did not fix the seed. Had we fixed the seed, we would get exactly same answers every time. Okay, so the one that normal equation predicted is not actually bad. It actually does a very good job, right? Utilizing the mathematical relationship of like differential calculus, that if we differentiate error and equate it to 0, the values that are going to be predicted are going to be close to original, right? So instead of saying that we have got perfect line, we say that we have got a line a line for which the error is minimum. Okay, we have drawn a straight line for which the error is minimum. Great, wonderful, wonderful. So that was our first step towards predictions. We learned two techniques. Now we can use this to do the prediction by by adding 1 to each instance and then doing the dot product, right? Remember xt xt dot the theta, that gives the answer, right? Great. So let's plot the model's prediction, and this is how it looks like. Okay, everybody is clear about it? Yes, please feel free to ask. Thank you, Deepak, for informing. Yes. All right, moving ahead. So we learned quite a few things. Now moving ahead. So the normal equation, basically when the normal linear regression actually does the same thing. Whatever we did just now, normal linear regression also does the same thing. Okay, so we can try the linear regression, right? Remember the linear regression, right? So, all right, let's try here. Okay. Now, since we have changed some of the variables, that's why we have, okay, let me try again. And what was it here? 2, right? We did actually set the, oh, how come? Is it because we ran this? Okay, this is some random thing. Let's just, interesting. So never mind. So I think these values, right? I think, are we making a mistake? This is the value. Let's skip it. Now this, let's skip this part also. Okay, so never mind. So now We could use the linear regression class and instantiate it and do the fit and then compute the intercept and the coefficient, right? And do the prediction. All right. So this way we get these values. Okay. So we can use the linear regression algorithm just like that and get the answer. All right. The normal equation computes the inverse of xt dot x transpose with a dot product with x, which is actually a complex mechanism, which is the x is essentially a n by n matrix. When you do xt dot x, it's essentially a n by n matrix, and when you do the inverse of it, the outcome is really complex, right? For solving the n consecutive equations with n variables, it takes O n cube. The complexity is O n cube. Therefore, as the number of features increase, the normal equation becomes slower and slower, right? Slower and slower. So in case, let's say there were 3 features, and the normal equation was taking say 10 seconds, right? 10 seconds. Let's say there was 3 features and normal equation was taking around 10 seconds. Now, if the features become 6, it will start taking 80 seconds. If the features become from 3, it become let's say 9, right? It'll start taking 27 times the actual time. That's the impact of O n cube, right? Therefore, if your data has too many features, it's going to be impossible. And in MNIST, how many columns we had? We had 786 columns, 784 columns, right? 784 columns. Now imagine if it was taking for one feature, let's say 1 second, for 784 columns, it's going to take 784 to the power 3, those many seconds, right? That's actually humongous, isn't it? In case of, let's say, MNIST, how many columns we had? 784, right? 784. And if for one column it took that much time, these many seconds, right? These many seconds, right? And these many hours, correct? These many hours, right? And these many days, and these many years, right? So you can see the impact. If for one column it was taking 1 second, it's going to take these many years for MNIST. All right, it's important to feel the meaning of O n cube by trying this kind of manipulation the way I just did, by increase the number and see what happens, right? It's very important to know the complexity and the impact of it. All right, so the complexity of normal equation is actually high, therefore it's not practical to use normal equation when the features are huge. If you double the number of features, then the computation gets increased by 8 times, and if you make the features 10 times, then the complexity increases by 1,000 times. The time it takes is going to be increased by 1,000 times. Now that's why normal equation gets very slow when the number of features grow larger. The normal equation is linear with regards to the number of instances in training set. So it handles large training set efficiently. If your number of records are really huge but your features are low, then you can use happily the normal equation. And but everything has to be loaded into the memory, right? Because it has to do all kinds of manipulations, and therefore the entire data must fit in the memory. So let's explore different ways to train a linear regression model which are better suited for cases where there are large number of features or too many training instances to fit in the memory, right? So normal equation cannot be used when there are too many features, and also the relationship between the data is nonlinear, right? Now, for such case, most practical thing to do is use the third technique called gradient descent. First technique was just solve the parallel equations and be happy. Second was normal equation. And third technique is gradient descent. Gradient descent is a wonderful technique, and almost every algorithm in one way or another uses gradient descent. All right. It's basically a greedy approach. Okay. It's essentially a greedy approach. And the way we learn gradient descent is that if you are lost in the mountains in a dense fog, you cannot see anything. You can only feel the slope on the ground below your feet, right? And you have to get to the bottom of the valley quickly. What are you going to do? Yes, feel the slope, correct, and take small steps downwards. Okay, so Robert says we'll take steps downwards, correct? That's right. Now my question is, if the slope is steep, will you go fast or will you go slow? If the slope is steep, you should go fast because you know that you are very, very sure that the deep side is this side. Okay? Because you're confident that that's the deep side. But let's say in case the slope is flatter, as in there is the slope is not that steep, then you stop or slow down, right? So that you don't bypass this. Okay? Or let me ask you this. Okay? Instead of taking steps, you were free to even take very, very long steps. Okay? Right now, the way we define step is how long can we walk, right? The steps. Imagine that you were free to jump anywhere, right? Free to jump anywhere. So in that case, when you know that it's a steep curve, you would like to go really fast or take a bigger step because 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 the chance of getting to the bottom is very high here. Therefore, the steeper the slope, the faster gradient descent goes. Okay? Take a step. If the step is downhill, keep walking the same direction, and otherwise reverse the direction. Okay? Reverse the direction and repeat the steps until you reach to the bottom. Okay, so this is what we're going to do. The learning step at every point, that learning step is bigger when the slope is steeper, smaller when the slope is kind of flat, right? Otherwise, it will never reach the minimum. Like you're about to reach the minimum, you'll only take smaller step. You'll not take really big step, otherwise you'll reach here. Then when you reach here, then you'll go back. And if your learning step is really big, then you will never reach the minimum. Good? Is it clear, everyone? Yes? Okay. And so essentially, it is a way of optimization, right? In the cases when you can feel the slope under your feet, you apply the gradient descent. All right. If you can find out the differential of the path then you can feel the slope and therefore you can use the gradient descent. Gradient descent measures the local gradient of the cost function. So whatever is the error, remember our first, the one that where we used that technique, we simply did dE by d theta 1 and equated it to 0, or d theta 2, theta naught equated to 0, right? Instead of that way, what we do is we do a little bit probe. We check some random value of theta, and then the slope, and in case it's going down, we go to that direction. All right. So we measure the local gradient, as in the gradient means the slope, as in the rate of change or differentiation or differential, with regards to the parameter vector theta, and it goes in the direction of descending gradient until the gradient becomes 0. We start by filling theta with random values. Initially, what we do is we just take any random values of theta, right? We assume some random value of theta, and then we improve these values gradually by taking one baby step at a time. Each step attempts to decrease the cost function until the algorithm converges to the minimum. Okay, so basically each step attempts to decrease the cost function, which is mean square error, until the algorithm converges to a minimum. Okay. In gradient descent, the size of steps, also called as learning rate, plays a very important role. Okay. If the learning rate was too small, then the algorithm will have to go through many iterations to converge. Okay. And if the learning rate is too high, what will happen is, let's say we are here and our learning rate is really big. So even though we know that we have to go down, we took really big steps. We went to the other side of minimum. And then when we went to the other side of minima, we realized that we were supposed to go back, right? And therefore, we took a bigger step again and again, and so on. So it kept on diverging instead of converging. Steps mean theta? No. Steps mean steps is a function of step is a function of learning rate and how much slope it is, right? So one is a fixed learning step multiplied by the rate of change of error with respect to theta. So all we are trying to do is we are trying to minimize the error by tweaking theta. Tweaking theta in such a way that it reduces the rate of it basically takes the rate of change of error to 0, right? If learning rate is too high, this might take a long time to converge. Therefore, larger and larger value failing, and it will fail to find a good solution. All right. Let me just show you. Oh, we don't have here. All right. Let me go back here. All right. So this is what happens. I'll just tell you. So it's actually really easy to actually write code for it. Okay. So this is how it is. So imagine that we had some error. We know how to compute error, right? We had some error. Okay. And what we do is we also compute the rate of change of error with respect to say theta naught. Okay. So we computed that. Now theta naught is going to be new theta naught. This is theta naught dash. This is the new value of theta. Whatever was there in the initial value of theta minus rate of change divided by this. All right. So what you see here is that this theta naught was the random value. So initially what we'll do is we'll say theta naught is random. Okay, we just assumed some value of theta naught. And then what we did was we said theta naught minus eta, and we multiply by rate of change of error with respect to theta naught. Now, if this rate is positive, meaning as the theta increases, error increases, correct? Therefore, we need to subtract theta, we need to decrease theta, okay? If the error rate is negative, as in when we increase theta, error comes down. In that case, this will be negative, and hence the theta will increase, because our overall objective is to bring down the error. So you can see that it's an iterative approach. Is it clear, Deepak? All right. So this is some fixed number. This is some fixed number. We can basically uh, give its value to any algorithm, and this is the learning rate. Eta is that learning rate. It's a constant. Okay, this is learning rate. Okay, so this learning rate is essentially a constant, and this is used, basically we try various hyperparameters, and learning rate, or the eta, is one of those. Now sometimes the error function might have multiple minimas. Okay, not every function is going to have that beautiful bowl, correct? And there may be holes, ridges, plateaus, and all sorts of irregular terrains, making convergence to the minimum very difficult. So a question from Deepak is, we vary this learning rate iteration wise? No, we don't vary learning rate much. Sometimes we do vary some of the algorithms, but it's very rare. We basically use the learning rate for training, and we try all possible ways by using the hyperparameter optimization. In hyperparameter optimization, we try different permutations of hyperparameters, but for one permutation, we finish the entire learning and then test it out. Okay, so iteration wise, it doesn't change, but it changes when we are trying the hyperparameter optimization. Our question is, I mean, steps, the steps value of theta 0, steps means changing in values between iterations. Okay, so steps basically, the learning rate remains same, the eta, while the step size changes. That's correct. Initially, if the slope is high, the step size is going to be really high. This is step size, this whole part is called step size generally, that every time we are reducing theta by this much. Okay. All right, moving ahead. So gradient descent faces a little bit of difficulty when it comes to irregular terrains, right? When we start here, the slope is there, correct? And slope is steep, so it'll go down and stop here, right? If let's say the initial values of theta were this, right? Because we are basically initializing the values of theta as random numbers. So initial value of thetas are basically, let's say here, then what will happen is suddenly, since the rate of change is steep, it'll go down this side and go down this side and keep on going, and will reach here. Now this is not optimum because this one is smaller than this. Okay, And the moment in case it comes down to here, it'll go back here because this is the side where the error is reducing. Here on the y-axis is the error, or x-axis is the theta. Similarly, if let's say we started somewhere here, we computed the slope. Slope is almost like 0. Therefore, it'll have a difficulty moving beyond here, correct? Because this is also a horizontal line, and rate of change of error with respect to theta is going to be 0, and therefore the theta will not change, and it will stop here. It will stop here, correct? So these are the difficult times of the gradient descent, when you have multiple minimas, and if you have the plateaus, right? Is everybody clear about this? A question from Deepak is not clear about relationship between slope change and learning rate and steps mathematically. All right, let me try again. Let me try again. Can I do? Yes, this is good. This is good. Okay. So you see that at every point of time, this is a classic example of the gradient descent. So we have got the xb, remember xb from our previous experiment, right? And the gradients in case of our data is this much. In case of linear regression, the gradients are calculated like this, okay? And initially we have taken theta as random value. As the iteration is going, as the iteration is going, what's happening is this theta is reducing this way. New theta is going to be theta minus eta multiplied by gradients. It could also increase because gradients might become 0. All right. So here what we are doing is we are assuming some value of learning rate, and number of iterations also we are saying 100, and number of instances is 100. So we are initially, theta is something that the model is. Theta is not the slope. Theta is the objective. Theta is what we are trying to find out, right? Slope is what? Slope is the error, the gradient with respect to the theta. The rate of change of error with respect to rate of change of gradients, okay? Because gradients is what we are going to vary. So we are saying that find out that error for which the gradients, find out the gradients for which error is almost like 0. Minimize error and find out thetas, okay? Find out thetas for the case where the error is minimum. So what we're doing is we're starting with the random value of theta. In case error increases, we decrease theta. In case error error starts increasing, then we decrease theta. If error starts decreasing, then start decreasing with theta increase, we keep on going in that direction. That's what is happening here. So we compute the rate of change of error with respect to theta, and that's called gradients. And what we are doing is we multiply these gradients with a constant that we define here, and that become, and subtract these values from theta, and that is new theta, right? So we are tweaking theta by how much? This value every time. We are changing theta by this value every time. Okay, if you change this to say 100, this change will be really big, and therefore it will not converge. Okay. All right, we're going to go over this again. So what we see is that if the step size is too big, what will happen? It will never converge and keep on diverging. Then the other problem with the gradient descent is that in case there are multiple minimas, then our function might get stuck somewhere here, right? If you are going on a mountain, you did not see all possible slopes, but you only see the current slope, you might get stuck in the local minima. Instead of reaching here, you will be satisfied here, right? And similarly here, if you're coming from this side, here the rate of change is going to be so slow that probably you are going to stop here. All right. Now, so if we start from left, the gradient descent converges to a minimum, which is not as good as the global minimum. And if we are starting from the right, it will take a long time to cross the plateau, and it will stop early. We will never reach the global minimum, right? The MSE, the mean square error, is a convex function, right? If we pick any 2 points on the curve, the line segment joining them never crosses the curve. Okay, what does it mean by convex function? Convex function generally looks like this, and convex function means if there is a line segment joining them. So if we take 2 points, this and this, and we draw a line segment, the line segment should never crosses the curve again, right? This line segment, we take a 2 points, this is going to be like this, right? It will never touch the line, this line segment will never touch the curve again other than these 2 points, right? This such kind of function is called convex function. Okay, convex function is the one where one line intersects at exactly 2 points, or maybe one. Okay, so when you are using the gradient descent, we should ensure that all features have similar scale. This is important criteria. Remember our standard scalar earlier, that our function should be our values of various features should be scaled. Otherwise, it will take a longer time to converge. All right. All right. Say for example, here the color of this graph is showing the cost or error, right? Okay, imagine that we have thetas and theta 1 and theta 2. Our objective is to find those values of thetas where the cost is minimum or error is minimum, right? So imagine that we draw this three-dimensional plot whereby on x-axis it's one theta and on y-axis is another, right? And here you can see that this somewhere, it's like a bowl. Okay, it's like a bowl. Here it's too high, here it's too low. Okay, so you're looking at the bowl from the top. It's like soup bowl. Here is the lowest point of the bowl, here is the highest point of the bowl. So this is the cost function drawn in the z direction, and theta 1 and theta 2. So we have to, wherever we start from the bowl, we have to roll down till the bottom, correct? We have to roll down till the bottom. That's the objective. Wherever we start at this bowl, meaning theta 1, theta 2, maybe here, maybe here, maybe here, but eventually we want to get down to the bottom of it, right? We want to go to that point of theta 1 and theta 2, or we want to figure out that model, figure out those weights. Theta 1, theta 2 is also called weights. We want to figure out those weights for which the cost is minimum, right? Cost is minimum. So if this is a perfect circular bowl, the chance of getting to the bottom is very high. But if it is stretched out, the chance is lower, right? Therefore, it's important to force various columns to come to the same scale. Okay? Therefore, it's important to do the feature scaling if you want to use the gradient descent. All right? Imagine that theta 1 and theta 2, they were on different scales. Okay, the impact of theta 1 and theta 2. So if the two values were on a different scale, this is how it looks like. Okay, therefore the reaching to the lowest of the lowest of the bowl will take a long time. All right. So gradient descent algorithm goes almost orthogonal to the direction of global minimum. And so if we have something like this, whereby you have, this is a stretched out bowl, in which what will happen is instead of we rolling down this side, we might roll down to this side and take long time, right? So it's going to have a long march in case there is a this kind of a bowl which is not uniform or circular or is not perfect bowl in the y direction. Okay, therefore make sure that you scale your feature. All right, this is how you can see it in the 3 dimensions. This is how you can see it in the 3 dimensions. And on z-axis it's the cost, on x and y it is feature 1 and feature 2. All right, basically it's an iterative approach in which what we do is we try to find out whether we want to go in that direction where our error is decreasing. Okay. All right. Again, remember that training a model means searching for the best possible model parameters, that is theta 0, theta 1, and so on. They are also called weights. And we have to find out such weights or thetas which basically minimize the cost like MSE, or which minimize the error like MSE, mean squared error. Algorithms will have to search in more dimensions if the model has more features, and the search becomes complex. Let's implement gradient descent now using some known algorithms such as batch gradient descent, stochastic gradient descent, and mini batch. So first one is a question from Robert is, what if you have local and global minimum? When does gradient descent stop? So it depends. In case you have global and local minimum, the gradient descent will be a function of where does it start from, right? And therefore, in case it's starting where it's local minima, it'll end up at local minima. If it's starting at global minima, it'll end up at global minima. So gradient descent has a tendency to stop at local minima and not move ahead. That's why there are variations to the gradient descent approach, and those are the ones that we are going to discuss. First one is the batch gradient descent. All right. So the way we implement batch gradient descent is, first of all, we initialize the model parameters theta 1, theta 2, and so on with some random values. And for each of the weights, we change one weight while keeping other weights fixed and calculate the change of cost. This is also known as partial derivative. A question from Jaya is, in case of some local and global minima, what will happen to the gradient descent? Okay, in case of same local and global minima, what will happen to the gradient descent? The gradient descent will be a function of where does it start. In case it found any of the global or local minima, it'll basically stop there. Okay, since it's greedy, it'll settle down very quickly with whatever it gets in the beginning. That's why we generally use stochastic gradient descent. All right. And in case we have multiple minimas, okay, or we try hyperparameter tuning. That way we would know that what's happening under the hood. All right, so if we have, like, we try the same algorithm multiple times and we see multiple outcomes, we basically pick the one that has given us the best outcome. All right, so there's there are some methods, some improvements to gradient descent that we'll study in deep learning again, like Nesterov and the momentum and so on. There are a couple of improvements to the gradient descent. All right. So if needed, we will actually cover it here. So partial derivative is when we are just moving to x-axis and not moving to the y-axis. Okay, so we basically compute the partial derivative like the way we computed earlier, that we would change only one value while keeping others fixed, right? And that's how the other values will be considered a constant and so on, right? So to implement gradient descent, we basically compute the partial derivative first, and it is like asking what is the slope of mountain under my feet if I face east, and then asking the same question by turning to the north, right? And we do that for all dimensions. So in general, we compute the gradient of the cost function with regards to each model parameter, right? So what we do is we compute, so what we do is we take the error function or cost function and compute the rate of change of the cost function with respect to each of the thetas, okay? Meaning find out how is this errors changing, how the error is changing with respect to theta 1, theta 2, theta 3, and so on. And based on that, based on those slopes, based on those rate of changes, we tweak the thetas. All right. Below is the equation of finding partial derivative of the cost function with respect to theta. So whatever we had studied earlier. So remember that we had theta t dot x, right, minus y and square, correct? So when we do the partial derivative, that square comes outside and this x comes outside, right? Because we are differentiating it with respect to theta, right? So remember that was 1 by m sigma theta t dot xi minus y, and then there was a square here, right? When we differentiate it with respect to theta, what happens is 2 comes out, right? So all right, those who are wondering, let's say y is x square. Ouch. Okay, let me try drawing it again in better way. Let's say this is y is equals to, why is it writing properly? Y equals to x square. So what is dy by dx? 2x, right? And what about 3x plus 1 whole square? So it's going to be 2 of 3 of x plus 1 into 3. Okay, right? So this is called chain rule. This is called chain rule. Okay, so we can also represent it like y equals x1 square and x1 equals 3 of, right, 3 of y, 3 of x2. Okay, so x1 equals 3 of x2 plus 1, right? We could also write it like this, right? So it'll be, when I say dy by dx, right, it'll be first, okay, this is x actually, okay, so it'll be, first of all, it'll be dy by dx1, right, multiplied by dx1 by dx and so on, right? That's how we compute. So dy by dx, this is x actually. So we are saying that first you differentiate y with respect to x1, and then you differentiate x1 with respect to x. All right, so that's how we are computing. This is what we have known earlier. So first of all, what we did was we computed the derivative of it, assuming that this is up full variable. So it'll 2 into this. Now then we differentiated this part, which is 3. So this became 18x plus 6. That's what we have done here. Remember that it was theta t dot this, and there was a square. That square went out, that became 2, and so on, right? So in this equation, we calculate the partial derivative of a vector like theta j, and so on, right? So here we are saying that first differentiate theta with respect to theta. First differentiate the MSE with theta 1, then theta 2, and theta 3. Okay? So when we do that, we get a vector of all the values, right? When we differentiated this, the error with respect to theta 1, then theta 2, then theta 3, we get these values, right? And we have 2 by m xt dot x dot 0 x dot theta minus y. This is what we get. Okay, so it's going to be a matrix, or you can say a vector containing multiple values, right? So this is our mean square error with respect to all theta. So this is essentially a vector, right? Now this formula involves calculation over the full training set X at every step. So what's happening here is that we are computing this mean square error. Okay, mean square error. Now this one will give us a vector where first one will contain the rate of change with respect to theta naught and so on, right? Since batch gradient descent uses the entire training data at every step, it's terribly slow on large training set. Okay, all right, but gradient descent scales well with number of features. It's faster to train linear regression model when there are thousands of features using gradient descent than using normal equations. So it's faster than normal equations. So this is what we're going to do. At every step, what are we going to do is we are going to compute the new thetas by this formula. Remember, this theta is basically list of thetas. This theta is basically list of thetas, and this error is basically list of errors in thetas, right? Rate of change of error is basically this list of rate of change of errors, which is basically a vector, and a vector. All right? So this is how it looks like. Using the gradient descent, we can create this is only for linear regression, right? Here we know the formula, so we are using the formula for computing the gradients. A number of times we don't know the formula, okay? In case we don't know the formula, what do we do? We use the finite values, okay? We use the finite values, and how do we do that? Quickly, anybody? If we don't know the formula, here we were very happy that we knew the formula of all the values and we were able to compute the gradients using this formula, correct? We use MSE and we knew that it's a linear regression, so we basically multiplied theta with x and then we computed the mean square error. But a number of times we do not know the formula, right? So we can always write a differentiation function, right? I'm just writing, let's say, a differentiation function right now. This is my differentiation function given a function f. This function will differentiate this f at value x. Okay, meaning it'll find the value of x, value of rate of change of f with respect to x. And how does it do that? Change x a little bit. Okay, change x a little bit. Let's call it, that little bit is how much? Let's say 0.0001, right? Change x a little bit and change x a little bit and subtract from the current position, okay? Divide by twice of d, okay? So this is the rate of change. So let's just check if my diff function is working fine. So I'm just showing you that in case we don't know the actual function, whatever it is. Okay, let's say we are defining a function called square, right? And we are returning x into x, right? Or let's say we are defining cube, okay, like this, right? And let's take a look at what is the differential of square when x equals to 2, right? Let me just correct this function. All right, now this is correct. So you see that at x equals to 1, the differential of x is 2x, right? This is 2, right? At x equals to 2, the differential is 2x, which is 4, and so on, right? Similarly, for the cube, for x cube, the differential is 3x squared, which is 3 into 4, which is 12. So you can see that even when we did not know how to calculate the differentiation, we can always calculate using this formula. Why this formula? It's essentially saying that change x a little bit, compute the function value, and and then differentiate that and compute the rate of change, right? This is what it is. We change it a little bit and measure the rate of change and so on. Because lots of us fear that we won't be able to compute the numeric differentiation, but it is very much possible. Okay, you can see that here how simple it is to calculate the differentiation of any value. Even if you don't know the formula, you can generally use this mechanism. All right, so we'll continue from here. I hope this is all clear to you. There might be some things that I'm repeating multiple times. I'm doing it purposefully, but you can let me know in case it's going too slow. All right, this is the important part, so that's why I'm taking the time. All right, because this will come in the neural networks also. Right, great. I look forward to see you in the next session at the same time. Bye bye. Have a good day.